Section 19.4. The origin of selection rules. Not all vibrational transitions are allowed. For harmonic oscillators, only the 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5 excitations, and the 1 to 0, 2 to 1, 3 to 2, 4 to 3, 5 to 4, etc. The excitations are allowed. So now you can tell that delta n must be plus minus 1. Either the quantum numbers increase by 1 or they decrease by 1. And this is the selection rule for the vibrational transition of a harmonic oscillator. So that means 0 to 2 transition is forbidden. 3 to 1 transition is also forbidden. So how do we get this selection rule? Well, we need to solve the time-dependent Schrodinger equation of the photon-induced M to N transition, and we learned the transition probability is proportional to the squared modulus of the transition dipole moment, and this is the notation. So Mn give you the initial and final quantum numbers. Mu is the notation for the dipole moment. X means we'll just put this diatomic molecule in the x-axis. And this transition dipole moment is an integral of psi of m times mu times psi of m. So it's a product of three terms. This is the complex conjugate of the wave function for the initial energy level, and this is the wave function of the final energy level n. In the middle, you have the dipole moment of the diatomic molecule. And we're putting this diatomic molecule in the x direction, so this is x. And now this x is the displacement in the x direction. Alright, so let's say, for example, HCl has an equilibrium bond distance of 1.275 angstroms. And then this molecule may vibrate. The distance may change to 1.276 angstroms. So X is 1.276 minus 1.275. You get 0.001 angstrom. That's the displacement. Alright, so again, we can calculate the transition probability from level M to level N, and this probability is proportional to this transition dipole moment squared. It's important because if we know this transition dipole moment is 0, then this transition is forbidden. If the transition dipole moment is non-zero, no matter it's negative or positive or even a complex number or imaginary number, not a problem. The probability is positive because, again, this probability is proportional to the squared modulus of the transition dipole moment. So the only condition we need to satisfy is this transition dipole moment cannot be 0. Now I'll give you an example. The vibrational transition of a homonuclear diatomic molecule is always forbidden. So you will never find O2, N2, H2 in an infrared spectrum. And here's the proof. We write out the integral here for the transition dipole moment. We have mu in the middle. Just remember, no matter how the O2, N2, or H2 molecule vibrates, what is its dipole moment? The dipole moment of O2, H2, N2 is always 0. No matter how you have this molecules vibrate. So this integral is 0, then you have a 0 transition dipole moment. That means the vibrational transition of a homonuclear diatomic molecule is always forbidden. Now let's look at HCl. Okay, this is a heteronuclear diatomic molecule, and the 0 to 1 transition is allowed. 0 to 2 is forbidden. Again, the selection rule is this. The quantum number, the vibrational quantum number, must change by 1. So over here, the quantum number changes by 2, so this is forbidden. I'm going to give you the wave functions of the first 3 lowest energy states for a harmonic oscillator. So over here, this is the lowest energy. You have a constant here times a Gaussian function. Over here, you have a constant times x times a Gaussian function. Here, you have a constant times 2 alpha x squared minus 1 times a Gaussian function. So the common factor is the Gaussian function, e to the power of negative alpha x squared over 2. If you don't remember what alpha is the square root of the product of k and mu. So square root of k mu. And then divided by h bar. Alpha has a unit. Alpha has a unit of meter to the power of negative 2. All right? And x has a unit of meter. So over here, these two together, you get a unitless number. Okay. Now let's look at this 3-wave functions again. So I want to tell you this: the first function, the lowest energy function, is an even function. That means if you change the sign of x, the function value remains unchanged. And this one, it's an odd function. If you change the sign of x, you will change the sign of the function. So it's an odd function. Over here, you get a even function again. If you change the sign of x, you're not going to change the value of this function. It's an even function again. So you probably can imagine those eigenfunctions will be even, and then odd, and then even, and then odd, and then even. All right? Okay. There's one more thing about these eigenfunctions. They have different eigenvalues, and if you took linear algebra, probably advanced linear algebra, you will see the Hermitian operator is a Hermitian operator, and the eigenfunctions of a Hermitian operator are always orthogonal to each other if they have different eigenvalues. So it's a complex statement. That means, if you look at these 3-wave functions, they have different eigenvalues. Half h nu, 1.5 h nu, and 2.5 h nu, they have different eigenvalues. And they are all eigenfunctions of a Hermitian operator, and then that means they are orthogonal to each other. So that means the integral of the product of any two of the 3-wave function is 0. So the integral of psi 0, psi 1 dx is 0. The integral of psi 1, psi 2 dx is 0. The integral of psi 0, psi 2 dx is also 0. So again, these 3 are eigenfunctions of the Hermitian operator, which happens to be a Hermitian operator. And they have different eigenvalues. And mathematically, we can prove that they are orthogonal to each other. Alright, now let's write the dipole moment of a oscillating molecule such as HCl. You have a partial charge on hydrogen, you have a partial charge on chlorine. So I'm going to using this delta E minus as the partial charge. And the dipole moment is the partial charge times the distance of separation. So this part is simply the distance between hydrogen and chlorine. It's not always equilibrium bond distance. Very often it's a little bit different from the equilibrium bond distance. That difference is displacement. So this x is displacement. Alright, so now we have the dipole moment. We have the eigenfunctions, wave functions. Now I'm going to prove this 0 to 2 transition is forbidden. How do we do that? Again, we evaluate this transition dipole moment from 0 to 2. Over here, the quantum number changes from 0 to 2. This is the initial wave function. This is the final wave function. In the middle, in the bold font, this is the dipole moment. So really, you just evaluate this integral. If it's 0, the transition is forbidden. If it's non-zero, that means the squared modulus of the integral is going to be positive. That means the probability is going to be positive. So how do we deal with this? Actually, I'm going to separate this integral to two different integrals. We have REQ here plus x here. So I'm going to say this delta E times REQ times this is going to be a constant C. All right, and then you have this Gaussian function here, this Gaussian function here, this polynomial function here. Okay, you see what I'm doing? I combine all the constants and put them together and call that C. Now let's look at the second term, plus x. Okay, we have x. Okay, it's a function of x. We have this guy, two Gaussian functions, and we have this polynomial function. So I'm going to multiply x by this polynomial function. I got this expression, and we have two Gaussian functions. What about this guy, and delta E? It's a constant, so I'm going to say it's D. All right? We don't even care about the values of C and D, because I will prove it to you. This integral is 0, and that integral is also 0. So first, this integral is 0 because we are looking at the integral of the product of two different eigenfunctions of the Hermitian operator. And again, the Hermitian operator is a Hermitian operator. It's a concept in linear algebra and perhaps advanced linear algebra. It tells us these two wave functions are orthogonal to each other. That means the integral of the product of side 0 and side 2 is 0. So this is just 0 based on linear algebra. Now let's look at this term. This term, well, if you look at this integral, it's going to be 0 as well. Well, only because you are integrating a odd function from negative infinity to positive infinity. The integral of any odd function from negative infinity to positive infinity is 0 because you have two parts. Okay, when you look at the integral on a graph, fx versus x graph, the integrals are just the area under the function curve. If you look at the left-hand side and right-hand side, okay, they look similar. They are anti-symmetrical to each other. They have the same magnitude but different signs. Therefore, if you see this kind of integrals of odd functions from negative infinity to positive infinity, from negative infinity to 0, you have a function value. From 0 to positive infinity, you have another value. These two values are opposite to each other. They cancel. So, again, this first integral, this integral is 0 because side 0 and side 2 are orthogonal to each other. All right, and this is 0 only because we're looking at an odd function. Again, all Hermitians in quantum mechanics are Hermitian operators. So if you're interested in learning something about Hermitian operators or more linear algebra, you can just look at this webpage. Okay, let's look at this. Hermitian operators. So you can take a look at this. But it's not required for this class. We can also derive this actually. Now you're looking at the integral of side 0 and side 2. I combined e to the power of negative alpha x squared over 2 twice. So it's here. And we have this guy minus this guy. So I separated these two integrals. And then I used variable substitution. I defined z to be the square root of alpha times x. This way alpha times x squared is z squared. So we have this two integrals. And it's possible to derive this integral. The result is the square root of pi. It's also possible to derive this one, which is also the square root of pi. So these two cancel. All right, you can also use Wolfram alpha to calculate the integral of this exponential function. All you need to do is open wolframalpha.com and enter this. Integrate e to the power of negative z squared from negative infinity to positive infinity. That's it. And you'll get the square root of pi. You can also do this one. You'll also get the square root of pi. Okay. All right, this one is 0 because we're integrating a odd function. I'm going to give you another odd function. So it's a different example. It's also an odd function, and you can see in this odd function, this function and this part are anti-symmetric. Okay, anti-symmetric. So if you look at this value, it's negative. Over here, it's positive, right? So these two are anti-symmetric. These two are anti-symmetric. This area and this area are anti-symmetric. This area and this area are anti-symmetric. So basically, this area and this area will cancel. This integral and this integral will cancel. This integral and this integral will cancel. All right. So again, if you are looking at an integral of an odd function from negative infinity to positive infinity, the value is 0. It does not have to be from negative infinity to positive infinity. If you have an integral of an odd function from negative L to positive L, the integral is 0. L can be any number. Okay, we can also derive this, I think. What you need to do is, again, this is an odd function, so we know it's 0. But we can do it step by step. We separate these two parts. We have x to the power of 3. Over here we have x. In front we have a coefficient. But don't worry about the coefficient. I'm about to prove this is 0, this is 0. Because, x to the power of 3 is an odd function. X is an odd function as well. So now we get this and this. How did I get this? Look. I'm just saying x to the power of 3 is x squared times x, right? And x times dx is 1/2 dx squared. I'll let you prove this. Again, x times dx is equal to 1/2 dx squared. All right? Now we'll just do variable substitution. Let's say x squared is just z. X squared is just z. Right? We have a bunch of z's. So x is from negative infinity to positive infinity, and z is x squared. Z is from negative infinity squared to positive infinity squared. So if you look at the lower and upper limits of z, they are the same. So anyway, this is 0, this is 0. In the end, the integral of this odd function is 0. We just proved that the transition dipole moment for the 0 to 2 transition is 0. Therefore, its squared modulus is 0. And we conclude this 0 to 2 transition is forbidden. Now let's look at 0 to 1 transition. So this is the transition dipole moment. This is the level 0. This is level 1 wave function. In the middle, we have the dipole moment. Again, there are two terms. I'm going to separate these two terms. Okay, this one and this one. All right. So now you can see R combine this constant, this delta E, this REQ, and this constant together into C. All right, so you have this function inside the integral. All right, and then I will combine this delta E and this constant all together. That's our D, and inside you have this Gaussian function. I copy that here. And then you have x times x, that's x squared over here, and then you have this one here. So we got two functions, and again, we are looking at the integral of two eigenfunctions of a Hermitian operator. So it's 0. And also, you can tell this is an odd function, so it's 0. So we just proved this integral is 0 twice in two different ways. Now I'm going to say this is non-zero. This is non-zero because you are integrating a even function. Not only it's an even function, the integral value of this function is positive on the left-hand side from negative infinity to 0. It's also positive from 0 to positive infinity range, so it's got to be positive. All right, so we can still evaluate this, though. Let's see. So over here, we just proved the first term is 0. So this is trivial. This is quite simple. The second term, let's look at the second term. We need to do some variable substitution here. So we need to introduce a alpha here, and alpha a square root of alpha here. So alpha here, square root of alpha here. We can't just arbitrarily put in one alpha and then a square root alpha here. We want to make sure this is mathematically correct. So outside I have alpha to the power of negative 1.5 here. And then we'll do variable substitution. We'll say this is my z, okay? Square root of alpha times x is my z. So I have this integral, and actually this integral is just square root of pi over 2. We can derive this. We can also use Wolfram alpha. Anyway, the value of this is square root of pi over 2. So this transition dipole moment is this, and this is non-zero. Again, what is d? D is this constant. I'm sorry, this constant times delta E, the charge, times this constant. That's d. All right, that's d. So anyway, this is non-zero for HCl or any other heteronuclear diatomic molecule, because you do need the partial charge, okay? You need a non-zero partial charge. So we just proved that this is non-zero, and therefore the squared modulus of the transition dipole moment is positive. That means the transition probability from 0 to 1 is non-zero. It's positive. It's possible to observe the vibrational transition of the HCl molecule from the lowest energy level to the second lowest energy level. All right?